So it's really great to see such a sizable crowd of like-minded people, and I think the presentation we have just gone through also seemed very interesting. I didn't understand much, but the slides looked very interesting. So I'd like to build a bit on that and also to take a step back and talk a bit more on general electromagnetics challenges we see in the automotive industry or when it comes to vehicles. So thanks again for the introduction, and thank you for making time for this. Yeah, let's get started. I think at the end we also have a bit of time for questions and answers. Yeah, first off, why are we doing this? Why is simulation important? Again, we have seen it in some of the slides before. With simulation, we can get intelligence about our product, about our design. We can get confidence about its function, that everything works as intended. We get insights, and all of this powers, we believe, powers innovation, and that's where simulation comes in. That's why simulation is very important. If you look at a car nowadays, we are talking about a very complex system. There's so many subsystems there, right? There's lots of electronics in there, more and more, in fact. So we have several components in an automobile. We have the chassis, we have the body, there's some interior, then there's the powertrain, and we have the electronics. So the last two categories, the powertrain and the electronics, this is where CST comes in, where it can really add value with simulation. So if we divide those two parts, powertrain and electronics, a bit further, we can basically split it up into sensors. You have a lot of sensors in your car. We have the battery. That, of course, has become very important with electric vehicles. Then we have the electric drive system. We have control units. We have cable harness. So there's actually a lot of cables inside a car. I always read that there supposedly are kilometers of cables inside the car. I still don't believe that. It's like it's just such a big amount, right? Such a high number, but this is really how much cable we have in cars today, and you can imagine all the issues you have there because of that. Maybe one other comment here, right? We've been talking or looking at electric vehicles, but I think it's very important to understand that electromagnetic simulation actually is not only applicable to electric vehicles. If you think about it, even in conventional cars with a combustion engine, you still have antennas, you still have your electronic systems, you have sensors and everything. So even there, there's quite a bit of electromagnetic simulation, and I just wanted to get this this out so that we all understand electromagnetic simulation is becoming or has become much more relevant with the introduction of electric vehicles, but it doesn't mean that until now it has not been applicable. So if we look at it, electric vehicles or the electronics that are being put into cars, there's been a positive trend. So electronics actually make up more and more of the total cost of the car. So it's becoming more and more important. And again, as you can imagine, if we put in more electronics, we also introduce more problems, and you would need more simulation, or you would need to look at it a bit more closely in order to make sure everything is right. So what we really need, right, what our electrical and electronic engineers need is a tool that allows them to very easily look at those things. And I think with CST, we have such a tool. We have a very easy to use GUI, a graphical user interface. You can import all kinds of mechanical files. So you can import the car itself. You can import the subsystems. We give you a range of numerical techniques. So those are the so-called solvers for those of you who have used CST before. And they're all specialized based on the application you're looking at. They're very efficient at that particular application, which in turn allows you to run the simulation as quickly as possible and get results that are as accurate as possible. And then what we also need is the workflows, of course, and we are working together with the industry very closely to develop those workflows, to streamline them, to make sure they are smooth and easy to follow. And again, we believe with CST we have found and introduced such a tool. So electronics and software drive most of the automotive innovation. So again, we have a lot of different components. There's a complex network of suppliers as well that design some of those systems. And yeah, at the end of the day, what we want to give to the customer is an enjoyable mobile experience. So this was a bit of an introduction. Let me show what I would be talking about in the coming minutes. I know we wanted to look at EMC and EMI. What I'll be touching on very quickly, though, is first communication systems in cars. Just to give you a bit of an overview, right? There's so many electromagnetics based systems or applications in a car. Just wanted to show those to you because I think they look really nicely. And then after that, we go on to the topic of electrification. So this is where we have the sensors. This is where we have the motors, the electric motors. And then lastly, I would be looking at the compliance issues we generally have in cars and show you a bit of the workflows we have. So the longer you stay, the more applications you will get to know that we have when it comes to electromagnetics and cars. And at the end, just very quickly also, this is going to be just one slide just to show you what we have beyond electromagnetics. What else you can simulate if that's of any interest to you. So let's get started. Let's quickly look at the communication part of it. We have external communication. Those are the communication systems outside. We have interior or the internal communication. Those are all the systems inside the car designed to function inside the car only, perhaps. And then we have radar as well. So just really quick, again, don't want to spend too much time on it. We have antennas. There's two questions when it comes to antennas. One is, how should it look? So that's the big design part of it. It needs to be well designed. And then, of course, where do I put it? And this is what we use CST for. We designed the antenna, we put it on the car where we think it would look nice, where it doesn't pose any problems with the car's aerodynamics, perhaps. And then, yeah, you would be able to get the simulation results. So here we typically look at the radiation pattern, and very important, and this is applicable to all kinds of electromagnetic simulation problems. The more input you give into the simulation, the more accurate your result will be. So here we see the antenna by itself only, but look at the radiation pattern if we put the antenna on the car. So it's quite different, and again, this is important to notice, and this is why you should always try to include as many details as possible when you do any kind of simulation, in fact. If we go inside the car, right, this here is a Bluetooth antenna, so we want to see where do we need to position it so that the coverage inside the car is good, so that I can get a connection to my mobile phone everywhere. And you see left some nice animations. You see without the driver, without any occupants inside the car, and on the right you see what's happening if there actually is a driver. So it's also quite different, and again, you want those systems to work when the person is inside the car, so you would probably be looking at the right kind of picture. We talk about specific absorption rates as well. Are those systems or antennas harmful to humans? So this is also a very important aspect that we can look at nowadays with simulation. Then just to show you one other application, this here is a radar system for which we also have a very nice workflow. So you see here two vehicles. There's a radar system on the one on the left, and then we simulate the wave propagation. And we have something called hybrid workflows inside CST. What this allows you to do is you first just simulate the radar system itself, because that thing needs a very dense mesh. It needs a high number of mesh cells to get an accurate representation. And then we basically capture the result. You see it here in the bottom of the screen in the center. We call this field source. So this is the result of the radar system simulation. And we then use one of our specialized solvers, in this case, the integral equation solver, to simulate this result, what's happening with it or how it's propagating if we put it onto the car. So this is a very nice concept we have for a lot of workflows that allow you to really shorten or break down the simulation into parts, and allow you also to do those massive kinds of simulation. A car is relatively big if you compare it to the wavelengths of those communication systems. It's electrically very big. So this is the challenge for simulation. This is why we have been developing and introducing those, we call it hybrid workflows. Okay, this is the picture of the radar system. Here we're talking about 77 gigahertz, but let me move to the next one. Again, here you see a bit more about this hybrid workflow. So this is where we would put it. Usually we would put it behind the bumper. And then again, the question, of course, is where do I position it? How does the geometry of the bumper, the material, affect its performance? So those are all very important questions when it comes to electromagnetic simulation. Really cool picture here of the radar system in action. So we simulate the rays. This is also has been done with one of our specialized solvers, the asymptotic solver. So really, really nice to analyze the coverage here. And we can also look at the reflections in green here. So yeah, very relevant and important to look at that. And eventually you'll get something like this. Again, just to show it to you, we get a radar image of the target vehicle. Red means a lot of energy has been reflected there, and blue means not so much energy has been reflected there. So this is great to, if you're designing this kind of system, in terms of where do you need to position it, at what angle do you need to install it, and so on. So very nice application here. Okay, so this was the first topic. Next up, we would be looking at a couple of other things. For example, sensors. We have wireless charging systems and motors. And at the end, when we're going to look at the compliance applications, you'll probably see how those things are going to be related. So all those systems, again, introduce some problems themselves. And yeah, we need to simulate them as a whole. So more and more sensors nowadays in cars. With electric vehicles, you see, or we might start to see wireless charging systems. And of course, there are electric motors. So when we look at sensor designs, there are different kinds of sensors. So for example, we have this capacitive sensors where you have an object that's being detected by looking at the changes in capacitance between those electrodes. So this is one kind of sensor you could have. Then we look at position systems. So we have angular and linear position sensors, where you look at the position of a coil relative to its mounting position. So you can measure that. You can look at changes in the inductance, and then again read out the according value. We have proximity sensors, again, where you look at coil properties, how they are affected. And then we have some reluctance-based speed sensors as well, for example. So all kinds of sensors you would find in a car nowadays. Another thing is the wireless charging, as I've mentioned. So here we see a simple wireless charging system. You have two coils, and then one could be installed, on the parking lot. The other would be installed on the bottom side of the car. And then again, what we want to know is it efficient? It needs to be as efficient as possible. Of course, you want to charge your car in as quickly as possible. And the other part is it safe? Is it harmful to the occupants, to the driver, the passengers, and so on? So two important topics. And again, with CST, you can look at that. So you can simulate the whole system with the car, with the person. We give you biomodels as well, and you can very nicely look into those things and design them. Okay, we can also look at multidisciplinary analysis or applications. For example, if we look at coil and system design, again, there's some safety questions and compliance questions that we need to look at. We look at the battery again, where you would need to look into cooling, the cell chemistry, and the supply system. Is it stable? Do I have a stable supply for my systems that I have in the car? Then, of course, the motor. So this one also can be very nicely simulated inside CST, and we're going to see later that the motor controller is actually one of the things that's very challenging to design for cars. That's one of the things where you would usually look at compliance issues or try to solve the compliance issues. Just to show it to you, here you see the startup process of an electric motors. We see its speed against time, and again, you would look at a couple of things. You would want it to have maximum torque, of course. You want the startup time to be as short as possible. You want the rotational speed to basically converge as quickly as possible. So those ripples there, you want to reduce them. Yeah, you might also look at, what if parts of my motor are damaged? How would this affect the startup or the performance of the motor? Of course, we can also look at braking. So here you see the inverse. Here we're braking, and yeah, again, we look at the time. How long does it take to brake the motor? How does it affect torque and speed? And again, what if a part of the motor is damaged? What's going to happen? Will it still be able to brake properly, and so on? Another thing is those efficiency maps we have, where we look at the torque against speed. Of course, initially you have a lot of torque, but then as you increase speed, the torque is not as high anymore. So those are also very nice simulation results that you can generate, that you can produce in order to optimize your motor. Okay, then the next topic, again, we've gone through a couple of applications already. The next topic is compliance, and the typical things we look at here are the cables, the cable harnesses we have, then the onboard electronics, for example, the motor control, which is always very important. That is typically the thing introducing the problems, and then we look at the susceptibility as well. All right. So I mentioned it in the beginning. You have a lot of cables inside the car. They're connected wildly. They're bundled together, right? And those cable harnesses, some are shielded, some may not be shielded. So this introduces a range of problems that we need to look at. And again, if you think about that in a car you have several kilometers of cables, so this is really a critical design aspect of your car. And this is why we need to simulate it. So here we have a car. This is one of the models we've been using, and then inside CST we have a specialized module that allows you to very nicely define cables, cross sections of them, and basically model all those cable harnesses. So here we have one type of cable, and yeah, this is connected to some point, but then we have another kind of cable where you also have smaller cables inside, and yeah, you see how they are connected. So the yellow points are what we call nodes. And yeah, those two wire harnesses basically go together and are being used for the simulation. Electrostatic discharge is one of the analysis you can look into here. So you have your cables, they are connected to your onboard systems, and yeah, you can imagine, right? You're driving, and then there's a charge building up because your clothes are rubbing against the driver's seat or whatever. Then you might stop at the gas station, or if it's an electric vehicle, you might stop for I don't know, at a place to charge it. So what happens if you open the lid there in order to connect it to power for charging, right? So here we have simulated an electrostatic discharge, and you see how it's propagating, which systems that may be affected, and then you can in turn try to bundle your cables differently, or shield them differently, or play around with those kinds of parameters, and see if the problems occurring due to this discharge improve or get worse. Just to mention, this might also introduce some safety problems. Imagine there's an electrostatic discharge and it accidentally triggers the airbag. So this is one of the reasons why this is very important. Okay, then the motor controller. Here we have a variable frequency drive that's used for controlling motors, for example, the ones you have in fuel pumps. There's motors in cooling and fans and everywhere, and we don't want those systems to interfere with each other. So this is one of the schematics. We can represent that in CST as well. And again, imagine you want to look into those things, like, are those systems interfering with each other? you have the schematic, but you need to build it, right? You need to assemble the PCB and everything. You have to do a measurement and so on. So this is very expensive to do, and this is why simulation is important. So you can take everything into this virtual environment and simulate it very quickly and basically get the same kinds of results you would get in a measurement. Typically, we look for the unintended function. So this is designed to do something, and then again, we want to see, is it interfering with any of the systems, and how does it affect them? When we look at the PCB here, typically, if you have the PCB layout itself, that's still not enough. So here you see the actual PCB, you see the layout, but when we talk about simulation, again, what we would typically do is we would include the entire PCB in 3D because, again, you want the simulation setup to be as close to reality or as close to the measurement as possible. So here you see we included the entire PCB, all its components on the schematic. We included the housing, and we would assign the materials accordingly as well. Just again to make sure it's as close to reality as possible, and this is very important in order to get accurate results. So here you see some of the simulation results. We were looking at the radiated emissions here, if I'm not mistaken, so there must have been some probes somewhere. You could also look at the conducted emissions, of course, and what you're looking for is, are they under the legal limit? So would they comply with the standards? Can I get my product certified? Can I bring it onto the market? And we want to use simulation for that, again, because those physical tests, measurements, imagine you need to do this measurement, it takes you half a day or so, but if you have set up the simulation, setting up the simulation might also take you a bit of time, but overall it will be much faster to do or to replicate if you have a small modification and need to run it again than if you would do the actual measurement, for which you also need a test chamber, by the way. So in the simulation, you can just model it or even simulate the chamber itself, as we're going to see. So yeah, with the simulation, we want to get some results to predict those emissions to be sure that they are compliant. And on the right, very nicely, you see in red the measurement, and you see in green the simulation results. And it's not 100% overlapping, but it doesn't need to. What you're usually looking for is the frequency. So you see those spikes, you see those peaks. You want to know what frequencies they are at. And there we see a very nice correlation, especially for the first few ones, which are the important ones, the high ones, the ones you would like to focus on. Then I mentioned it, we can also look at anechoic chambers. So this is actually one of our clients who has used CST to design their measurement setup. So they were looking at building an anechoic chamber, and they modeled it inside CST. So on the right, you see the CST model. They have the table there. They have a test antenna on the right, some horn antenna, and they modeled all the absorber. They characterized their materials. So a very nice application here, which they have designed with CST. If we look at the same setup here, they have used some PCB that they have included in this chamber in the simulation. And you see the the wave propagation here. And yeah, again, the aim is to have confident predictions. You want to know, does it comply with your standards or not? Of course, you still need the measurement at the end, but you can get a lot of things done through simulation. The other thing is, if you're simulating all those systems, usually it's not necessary to model the entire car. Usually it's sufficient if you take a part of it, for example, the half of it, or just the part where you're installing the systems on, the motor controller and its immediate environment or surrounding. So this can also help you to really break down the simulation time. And you see on the right the gray materials. So I think they used ideal. They used PEC as the material, again, just to get an initial simulation done, which also runs much faster than if you're using lossy material. So this helps you to do a first simulation, and then you could, yeah, you would see, okay, this part of the car is not necessary to be included in the simulation because only the front of it is affecting my motor controller performance or my electronic system performance. So you can break it down and at the end have like a little bit of a simplified setup where you could then still use the accurate material representations. Yeah, some clients or companies, they have very big chambers that they are using, where they put in cars for measurements and so on. So again, we can all imagine how expensive those measurements are. If you need to, having the chamber already is very expensive, but then booking it for a whole day or for half a day to do this kind of measurement. And yeah, this is really where virtual testing is not only faster, but also less expensive. So we can do the same setup, but in a much easier way. You see on the right, we can just model the antenna itself. For example, from Antenna Magus, this is our antenna template library, very nice software, and then include the car and do the same kind of simulation. And it's also accurate. It's not only fast and less expensive, it's also accurate. So here you see one comparison where we simulated the sensor, and yeah, you see it against the frequency, and it correlates quite well. So we can say that virtual testing is accurate or accurate enough for our kinds of applications. Yeah, then maybe just to mention it a bit, I hope was an interesting overview so far. We can also go beyond electromagnetic, so we have a range of tools. We not only have CST. If we go around the circle really quick, we also have a software called SIMPAC for multi-body dynamics analysis. So there you could really patch together your car, all the systems, and simulate them together. Then we have a tool called Abacus for mechanical simulation. This is also a very nice software. For example, if you want to do crash test simulation, structural analysis, and so on, then there's a software called Wave 6 for vibroacoustics. So this is also has been very important, of course, for the experience of having or driving a car. That allows you to look into those kinds of things. And lastly, we have a software called XFlow, with which you could look at aerodynamics of a car. You can look at your air conditioning inside the car, how it flows. So this is our CFD simulation software. So it's not only CST. That's another thing I would like you to keep in mind. We have a range of tools for basically all kinds of physics that are out there. And this is the last slide. I would like to conclude this second part of the presentation, just to show you some of those other kinds of simulation in action. So on the top left, we have SimPack, where we set up a simulation of a car. There's some obstacles, and then we want to simulate the drivetrain, how it reacts, and so on. And yeah, the other applications, you see the radar system again, we have touched on really quick, and so on. So a lot of different applications and workflows that you can do. And yeah, thank you very much for listening, for making time for this. I hope it was an interesting overview. And yeah, I'll just hand it back to Kat. I believe we have a bit of time for Q&A. Of course, you're also welcome to reach out to us after this if you have a question later on. So thank you very much, and back to you, Kat.